Okay, so before we continue the session, please you have to run in advance this script, right? The MLS.sa. So as you see, I was running this, right? So this one, MLS, this one. So we're running this, and the output of this will be here, right? So the MLS this here. So there is the output files that you get. I just sent the email today in the morning about the results you have to get. In my case, my calculation lasts 878 seconds in total. So that is my calculation. I don't know what happens with yours. And the output, one of the output files is this, right? So in my case, I got this output file. This output is not cannot be exactly the same as yours, right? So okay, so I was running just today just before coming here, so I was getting this and that was it was 250 steps as you can see here. In my case, the final temperature was 342, right? So that was this that was this. My result. Okay, so that is it. So I don't know if you were able to run. So I don't know how this will happen to you. I will pause here just in case want to check any part. Okay. Okay, now what is next is that we are going to take the structure. The final structure in my simulation was this. So it was at 342 Kelvin. So I'm going to take this as a structure that is here, the Concar file. Where is this? The this Concar file. This Concar file, it is at that temperature. In my case, in your case, maybe it's other temperature, and you're going to have a different Concar file. So the Concar file you have cannot be exactly the same as it is here. But if you like, we can check it. Please open the contract file and check that you have these symbols, right? In my case, it does not appear these the levels that are here, right? So check that before you open this in ASE, check that you have these, right? That it has just silicon and hydrogen, okay? And after this, you can, you see, open this. And let's see how does it look, this structure, right? So let me see what is happening. As you can see, this is the status of my structure, right? Okay, as you can see, there is some broken symmetries, as you can see, so that doesn't matter. Anyways, this structure will be my initial starting point to do a simulated annealing. So simulated annealing is that I'm going to drop the temperature slowly to get almost to 0 Kelvin. So that's the only my only task, right? As you can see, if you see in your calculations, the structure is not exactly the same, be a little bit different. But the point is that you see these atoms here were fixed all the time. In my training, I fixed this silicon and this hydrogen atom. But the point is that in my training, I get a more realistic, setup. So that's the reason my force field is more realistic because it has the information about these hydrogens that are fixed here, but also these undercoordinated silicon. We call this silicon dimers. It has information. That's the reason why these complement the force field that we already generated about the bulk. That's it. Okay. So let's see. Okay. Anyone, please? I'm going to stop for a moment here. Any question, please? Somebody? Okay, so before I continue, please, we're going to start a simulated annealing calculation, right? But look, in the MLS, we have the Concar file that I just opened before. If you see the Concar file, you have the information about the coordinates of the atoms. But here below, here you see, this is information about the velocities of the atom, right? Because since this is at certain temperatures, in my case, this is a temperature of, how much is this? It's 250 Kelvin. So this is reflected in the velocities of these atoms. Okay? The velocities of these atoms. That is here in the second part, in the second section. So we don't erase it, right? That's the reason when a simulated annealing is going to have to, is that when we do a simulated annealing, you have to provide some temperature for the structure. Since we don't measure, we're going to see in a moment, we're not going to measure the initial temperature because the initial temperature depends on, in every one of these, right? In my case, it's this that is related 342 Kelvin here, right? So in your case, it will be different, but that's the reason why we should have different values here. And the point is that we have, the temperature was affected by certain temperature that you have in the simulation, right? Why we're doing this? Because we wanted to break symmetry in the system and to see, you know, by machine learning to find out some structure, you know, that we are going to use. Okay. Once we have this, please, after this machine learning is finished, we are going to continue with the simulated annealing. We are going to bring the system to near 0 Kelvin. Okay, and for this we are going to run this. But look this. So we are going to run this sa.sh, right? So look this, you should have this in this directory, right? I just shared with you this one. You see? I shared with you with this. Okay, so there it is, the script. Check that you have that script. In my case, I'm going to change the course. I'm going to change the course to 4, please. So I'm going to put here course. In my case, please, you don't have to do this. 4, right? And there it is, you see? So first of all, just let's understand what it's going to do. It's going to do a symbolic link of this file. That is the force field that we created during the machine learning of the slab, of the surface, you see? That's the reason why it looks in the MLS, it looks for this file, okay? Also, you see, it's going to copy the Concar file you generated in the last step of your machine learning training to Postcar file, and it's going to use this Incar SA. Well, look this Incar SA. Incar SA is this, okay? You see? Look this, I switch off the symmetry because I don't want to impose any symmetry constraints. You see, I use IDPOL, always very important. On surfaces, you have always to have this tab. And finally, for the simulated annealing, I'm going to do an NDT molecular dynamics, right? Look this, I have put here only the final temperature. I didn't put 0. I just put 0.1 Kelvin. That was okay. Okay, and the rest we keep the same. Okay, so I shared this file by the way. So let's run it, please. The simulated annealing is going to be fast because it is only using what's the name? The force field that we just ran. So please let's run it this. Simulated annealing. There it is, it's running, and it's going to be very fast. So I'm going to pause here the calculation. So one is finished, as you can see here. A folder SA is generated. You see here, and let's see the results. It says so. There is the result. In my case, it takes 10 seconds to complete the simulation of 300 steps.